Hello everyone, welcome to another Weather Wednesday. Quick, let me take your temperature. Yep, you guys are looking healthy, you're looking good. Today's topic is what is temperature and where did these Fahrenheit, Celsius, Kelvin, where did these scales, these temperature scales come from? That's what I want to talk about today, and also how these temperature scales might relate to space, because we are here at the Space Foundation. So we're going to use our Science on a Sphere here just to talk a little bit about temperature, talk about the history of these temperature scales, and then take a look forward at some forecasts around the world here. So let's begin with talking about the very beginning. So where to begin is, let's talk about Daniel Gabriel Fahrenheit. Okay, Daniel Fahrenheit was a Polish and Dutch scientist that lived in, let me get my notes here. He was born in 1686, long time ago, so early 1700s. He was working as a glass blower. So he was working with glass, creating glass apparatus, both for scientific equipment, and he was the first to, he's credited as the first to invent the mercury thermometer. So using mercury as the liquid or the medium that expands as it warms up. Let me put my thermometer down here and get my other thermometer here. So you guys may have seen a thermometer like this around. Many times they might have a scale of Fahrenheit or Celsius on them. So how did Fahrenheit come up with his temperature scale? What did he base it on? So first, he based it on, legend has it that he based it on the coldest day that he experienced in the Netherlands. But in order to get a consistent cold temperature, now imagine back in the 1700s, you don't have a refrigerator. You don't have a freezer. You can't artificially create ice. So what he did is, to create the lowest temperature possible, he took an ice water slurry and mixed a special salt in it to lower the freezing temperature. So this salt water brine is what it's called, was measured as the 0 point on his Fahrenheit scale. Today we measure that as about 4 degrees actually Fahrenheit, using more update scientific experiments or scientific equipment. But Fahrenheit, he proposed that this saltwater brine was the 0. Now what's the high? What's the highest level? Well, that is the human body. So using his mercury thermometer, he was able to get pretty close to the human body temperature, which was about 96 degrees Fahrenheit. He averaged that or moved that to about 100 degrees. So from 0 to 100, his 100, he measured the scale of the human body. Now, also the third point, if there was another point, that would be a very convenient point, which we'll see later, is the temperature at which water freezes. So when liquid water turns into solid water, he measured that as about 30 degrees Fahrenheit. Okay, so 30 degrees Fahrenheit, that was his third point for measuring temperature. Now, Daniel Fahrenheit, when he created this Fahrenheit scale, he based his work also off of another scientist named Ole Romer at the time, who was also trying to measure temperature, trying to become very accurate with temperature. So he kind of based his scale on Ole Romer's scale. So as I mentioned, the human body temperature, that was the high point. And then we have the different Fahrenheit and Celsius. So let's take a look at the Celsius scale. Celsius is based on, Celsius was first created by the astronomer, the Swedish astronomer named Anders Celsius. Okay, so he was Anders Celsius, born in 1701. He was the son of an astronomy professor and the grandson of a mathematician. So early on in his life, Anders Celsius, and let's move on to my next set of pictures here to see Anders Celsius here. Early on in his life, he demonstrated that he was very good with math. In fact, he calculated the curvature of the Earth very accurately. He also calculated the distance from the Earth to the sun very accurately too. So he was very good at measurement. Well, he first proposed, another thing too, which is kind of interesting, his astronomy discoveries. He also was the first to propose that the aurora borealis, the northern lights, had something to do with the Earth's magnetic field. That as the Earth's magnetic field changed, that influenced the northern lights. Now, why would he study that? Because remember, he's from Sweden. So he's from up north, and this also influenced his research in temperature scales. So Anders Celsius based his temperature scale, his thermometer, on water. He established that the freezing point of water be 100 and the boiling point of water be 0. So that sounds backwards, doesn't it? Well, Anders Celsius, he created this, and he first named this scale the centigrade scale. Centigrade, centi means 100. Grade means like gradient or steps. So 100 steps from the freezing point of water to the boiling point of water. But he first proposed that 100 be the freezing point of water. Why 100 the freezing point? I don't know. Maybe he lived in a cold place. Maybe that's why. But he proposed that 100 be the freezing point of water and 0 being the boiling point of water. He developed this Celsius scale in 1743 and proposed that. Unfortunately, he passed away in 1744, only at the age of 43 years old. And then the scientists after him, there's some dispute as whether it was Carl Linnaeus or Jean-Pierre Christine, who it was that changed. They flipped the scale from 0 being the boiling point to 0 being the freezing point of water. They flipped the scale and then named it after Celsius in honor of him. So Anders Celsius, very important person for both the Celsius scale for developing a temperature system, as well as for his astronomy too. He's the first to propose that the Earth's magnetic field had something to do with the aurora borealis. So there is your link between the Celsius scale and astronomy. Now, moving on, there are other temperature scales. So we have several temperature scales that have been used in science. One of those is Fahrenheit, another is Celsius, another is Kelvin. You also have a temperature scale of the Rankine, the Delisle, the Newton, the Ramer, which I mentioned. And then we also have the joule and calorie, which is a measurement of the amount of heat energy that something has, or something that can hold on to. So we measure food in calories. And calories, that's the amount of heat that's stored in that energy. Well, this guy, his name right now is Lord Kelvin, which is what the Kelvin temperature scale was based on. He was born William Thomson back in 1843. And William Thomson, he was also a mathematician and scientist. He was knighted as Sir William by Queen Victoria in 1866, and then ennobled in 1892 for his scientific work. He became ennobled as Baron Kelvin. He was named Kelvin after the river Kelvin that flowed past his laboratory in Glasgow. So he was Lord Kelvin, born William Thomson. He was tutored at home. He was taught at home by his father, who was a teacher of math and engineering. In 1848, he proposed the value of absolute zero. So he was the one that came up with the idea that the energy that a molecule has will eventually come to zero. His physical work also was in the realm of thermodynamics. So his work then contributed to the first and second laws of thermodynamics. Second law of thermodynamics says that heat always goes from hot to cold. So it always travels from hot to cold. Now this is very important for weather. As we've talked about this, heat always travels from hot to cold. Now cold also is more dense. Okay, so cold is more dense. So the cold air has more pressure than the warm air. Warm air rises and expands. Cold air sinks, but heat goes from hot to cold. That's the second law of thermodynamics. So Kelvin proposed this idea of absolute zero and then created that, then measured what is the temperature of absolute zero on the Celsius scale. And he measured that as minus 273.15 degrees Celsius. And that temperature stands even today. So mathematically, he proved what the temperature of absolute zero is. So let's talk just real quickly about what absolute zero is, because this is really one of those interesting things in physics. And I have something to demonstrate here. So here I have a molecule, not necessarily, an atom. Atoms typically aren't this big, but let's say this is a nucleus of an atom, the very center point. And the nucleus of an atom is always vibrating. It always has a little bit of energy, always moving around. The protons and neutrons in there are always moving around. And then going around the atom are these little electrons. These electrons have energy and motion as they're moving around this atom. Well, as temperature, as I've mentioned before, is a measurement of how much energy a molecule or atom has. So imagine if you could take the energy away from this atom, what would happen? What would happen if we slowed, or if we basically took this energy away so that these particles of the atom slowed to a stop? What would happen? Now, physically, we can't make that happen because of gravity and because just of the nature of surroundings. You can't take all the energy away from an atom, but you can get very, very close. And that's where this picture behind me, comes from. This picture right here is a measurement of this idea, of this concept that you can slow atoms down to zero. This is called a Bose-Einstein condensate. That is a fancy name named after a couple scientists, of course Einstein in there. But this Bose-Einstein condensate is the closest that humans have ever come to absolute zero. And the atoms and molecules behave very differently at this temperature, where scientists have said that it is the fifth state of matter. So we have solid, liquid, gas. Out in space, we have plasma. That's 4. The fifth state of matter is Bose-Einstein condensate. And that's what happens when you get your molecules or temperature as close to zero as possible. So very interesting stuff there as relates to temperature. Now, how does that apply to space? The last term that I want to share with you guys is the idea of black body radiation. So black body radiation is the measurement of the temperature or heat that a star is putting out. So you can see behind me, this is the Milky Way galaxy. It's a picture of the Milky Way galaxy. There's millions of stars behind me. How do we know how big these stars are, and how do we know how hot these stars are if we're measuring from millions and millions of miles away? We look at what's called the black body radiation. there is there's a relationship between the temperature that the star is giving off and the wavelength or the color that the star is giving off. And you can measure how hot that star is, and thus you can measure kind of where it is on its star cycle by measuring its wavelength, its color. So scientists use blackbody radiation, which is related to temperature, to see how old and how big stars are in space. So there's your temperature and space correlation. Let's finish up this Weather Wednesday today by taking a quick look at our forecast around the world. So bringing up clouds real time, this is what it's like right now. So here's the United States. Fast forwarding to today's date, the 21st, we can see there is a small hurricane out in the Atlantic Ocean out there. We have some clouds that are moving across the northern part of the United States. Because it's moving side to side like that, we can see that the northern part here is cold. The southern part is probably warm. That's what happens when the jet stream dips down like that. In order to look at the forecast, I'm going to bring up our wind streamers here. Let's bring up our wind streamers to take a look at the forecast model. So what does Science on a Sphere tell me is going to happen over the next several days? And so here is the United States here. Let me see if I can overlay the states. Nope, not that one. Here we go. Let's go American states right here. Okay, so here is overlaying that. Awesome. So looking ahead, we can see that on October 25th and 26th, right here, we're going to get a dip in the jet stream. So that dip is going to bring cold air. It's going to bring cold air from the North Canada down into the Midwestern states here. Also, what I notice as I bring the data set back here, also what I notice is that the West Coast is going to have a high pressure. The West Coast is going to have a high pressure system off the coast here. See how that's rotating to the right? So that's a high pressure system pushing, that's a ridge of pressure pushing and forcing this low pressure to drop down over the Midwest. So the October 25th and 26th, that's going to be the beginning of some weather change. Right now, it's pretty cool on over the Northwest, pretty cool over the North Central. That's what the current weather is. And then in the future, it's going to, on October 25th and 26th, it's going to drop down into the United States, that cold air. It's going to get some sunny weather on the West Coast. And it looks like there's another high pressure system over Mexico that is going to create more sunny weather, possibly some afternoon thunderstorms, but warmer temperatures over the southeast as we go into October 25th there. So that is looking forward at the forecast for the area. Now also, because of that dip in pressure, actually, let me bring up one last one here as I wrap this up. Here is the closer to us as far as the pressure goes. Look at that system drop down here in Colorado. So this is for us here in the Midwest. That system dropping down to Colorado looks like it's going to go all the way down to Texas, bringing cold air. Over the 26th, 27th, 28th, let me back that up. Let's see, that is a 26th. Going into the 27th. Guys, that's going to be some cold air, some good chance of snow, and whatever the 26th, 27th, I think that's like Monday or Tuesday. That's going to be a good chance for some snow. So this weekend, if you live in Colorado or the Midwest, make sure your sprinkler systems are blown out. Make sure your flower beds are ready to go, ready for some snow, because it's going to get cold on the 26th and 27th. So that's your forecast for now. Well, if you would like to know what's going on around your area, reach out to us on our social media pages. Also, we look forward to seeing you on our virtual home study day next week. So if you want to take a look at our our science and STEM activities for our home study day. Take a look for that for next Wednesday. Thank you guys for joining me today and learning a little bit about the history behind the temperature